Okay, in section 2, we're going to talk about functions in a more detailed aspect. So I have two definitions here that I'd like to go over. And the first one deals with this thing called domain. So the complete set of all possible values of the independent variable is called the domain. And then the second definition, the complete set of all possible values of the dependent variable, is called the range. All right. Now, I think a picture is a lot more advantageous than just writing on the wall. So let me show you what we mean by domain and range here. So I'm going to just pull this down. So here's Desmos here. And I'm going to type in a function that we all know, which is x to the second power. Okay. So let me kind of just clean this up here a little bit. All right, we're going to zoom in here a little bit. I think that looks pretty good. And we're going to copy and paste this into our notes. Oops. I don't know why my computer does that. All right, sorry about that. Here we go. All right. Now, across the x-axis, we call this our independent variable. All right. This is going to be our domain. All right. So as you can see here, if I'm on the x-axis and I'm just like walking to the left or to the right, please note that no matter which direction I walk along the x-axis, if I look up in the air, I will still see my function. No matter where I walk, I'm still going to see my function up above me because these arrows go on forever, right? So what we would say is the possible set of all the independent variables here, which is our domain, we would say the domain is negative infinity to positive infinity. That's the interval notation for this. And that's because I can use any independent value I want. I can use any x value, and f of x, which equals x to the second, will always have exactly one answer. All right, always exactly have one answer. Now, let's think about the range. The range, I'm going to change my marker here. The range will be all of the y values. So this is our dependent variable. This is the y-axis. We call this the range. And if I walk along this y-axis, please note that the lowest y value that I can get is going to be 0. And I use the bracket because I can include 0 because this point right here at the origin is defined, meaning it's included. So that's the lowest I can get. However, if I walk up, notice that since both arrows keep going up to positive y values, this will go to positive infinity. So this is what we really mean by domain and range. Now, I know some of you are probably sitting there thinking, boy, that was really easy. Is it always that simple? And obviously the answer to that question is no. So I want to grab Desmos again because I want to show you another function where our domain and range kind of get a little weird. So here's Desmos. And I'm going to go ahead and do the square root of x. Okay. So once again, we'll copy and paste this into our notes. All right. So from here, this is f of x equals the square root of x. And this happened in the previous problem, but this problem I really want to to kind of look at this. Here we have what we call a restricted domain. Now remember, domains are input independent, or you can call them X values, all right? If we look at this, notice that along the x-axis, we start all the way down there at the origin. Notice the square root, and if we think about this, square roots are never negative numbers, right? They're never negative. In fact, even your calculator knows that. So if you got your calculator out here, here's my fancy calculator. If it ever loads, there we go. And I'll just detach the LCD so we can see it. So even your calculator knows, hey, square root of -4. It says, wait a minute, that's a non-real answer. That doesn't mean an answer doesn't exist. It means the answer is non-real, okay? In fact, the square root of -4 is 2i. It's an imaginary number. But anyways, our domain in this situation is going to be restricted. So our domain, once again, picture yourself walking on the x-axis. How far to the left can you go? Well, I can get all the way to 0 because I know the square root of 0 is 0. How far in the positive x direction? Well, that's going to be positive infinity. So this is our restricted domain. And whenever you have a restricted domain, so restricted domains influence the range. And hopefully that makes sense, because when you think of the range, all right, that is the dependent variable. It depends on what x is. So our range in this scenario is also 0 to infinity, because you can see that this blue line is going to continuously get positive in the y direction. It just does it in a very slow manner. So we can kind of think of it this way. Domains are, how do I want to say this here? Domains are, I'm just going to say it. This is what I was thinking. I guess I don't have to make this video perfect, but domains are kind of funny. And the reason is we must find any exceptions. That's the biggie, all right? So when you have a picture, boy, that's really easy to do it. But now the question becomes, what if you don't? All right, so let's think about this. Let's find the domain for f of x equals 3x plus 1, my favorite function example. Well, if you think about this, this is nothing more than a linear function, which falls underneath the umbrella of polynomials. I'm going to give you a little, this is like a little morsel of information. All polynomials have the domain of -infinity to positive infinity. So as long as you got a polynomial, that's what your domain will always be. So I'm just going to give you some examples real quick. These are all polynomials. All right. Even my favorite, 3x plus 1. These are all polynomials, which means the domain is going to be -infinity to positive infinity, no matter what. It's when you start dealing with different types of functions that you got to be careful. And that's going to be this example right here. So if I want to find a domain for f of x equals 3 over 2x minus 1, I need to be careful with this. And that's because we got a denominator, and we cannot have a 0 as a denominator, because then we have something that is undefined, okay? So how do we find the domain for this? Well, since we cannot have 0 in our denominator, what we're going to do is we're going to take that denominator, we're going to set it equal to 0, and we're going to find out what number actually makes this 0. So if I just solve for x, what I have found is this, and this is how we always phrase domains, all right? I'm going to zoom out here just a little bit. What we write, and I'm just going to write domain, and then like a colon. So our domain for this problem, f of x equals 3 over 2x minus 1, is going to be all real numbers except x cannot equal 1/2. Because what ends up happening is if x is 1/2, you get 0 in that denominator. And that completely breaks that function. So once again, think about it in terms of a calculator. If your calculator was 3 over 2x minus 1, you hit 1/2 and then hit enter, the calculator is not going to work. And that's because this number is not in the domain. So when we go to find domains, it's better to find the exceptions versus trying to figure out what numbers actually work. Because there's an infinite amount of numbers. So you find the exception. So here's another example. How about let's find a domain for the square root of, you know what, let's make this prettier. 7x minus 14, and you'll see why I want to make it prettier here in a second. So when we look at this problem, we have a square root. We know underneath the radical, the only types of numbers we're allowed to have are positive. So how do we find the exceptions for a square root? You take the radicand, in this case it's 7x minus 14, and you're going to set this greater than or equal to 0, because great numbers that are greater than or equal to 0 are considered to be positive. All right. Now, if I just go ahead and solve this, I will add 14 to both sides. And finally divide both sides by 7 to give me this x is greater than or equal to 2. So my domain for p of x, which is equal to the square root of 7x minus 14, is all real numbers, comma, x must be greater than or equal to 2. Now, let me show you how and why this makes absolute sense. Now that we know the only independent variables we are allowed to use, the only independent values are going to be the number 2 or larger, watch what happens when you graph this. So here's Desmos again. We're going to graph this. So we got the square root of 7x minus 14, and watch. Look how that function shifted over 2 units to the right. And that's because this is where the domain starts. So the domain is going to be any x value you want. but it has to start at 2 and stay positive. So I hope this makes a lot more sense when we talk about domain. And when we talk about restricted domains, we see this all the time. For example, here's a great example right here, okay? All right, so we have a function. Let's say it's going to be height. So the function h of t, which equals 40t minus 9.8 t to the second, models a projectile's height at any time t. All right. So here's what I'm going to do. I'm going to graph this in Desmos so we can get a visual understanding of what's happening. Okay. So let's go back to Desmos. And unfortunately, Desmos, I don't think it understands t. Maybe it does. We're going to find out here in a second. How about that? So I'm just going to type in y equals, and it was 40t minus 9.8 t to the second power. And I'm going to fix this a little bit. How high does this get? 40? Okay, yeah, I thought so. So give me 1 second here. I'm sorry. Yeah, okay. So I'm just fixing this to make it look pretty. So we're going to go from -2 to 10 in the x, or in the independent variable. And then for y, I'm going to go -5 to 55. All right. So I think this looks so much better. And we'll copy and paste this once again into our notes. All right. So here's what we mean by a restricted domain, okay? This is the function h of t, which equals 40t minus 9.8 t to the second. And to be honest with you, I do not care at all about this space down here. I don't care at all about anything below the y-axis, or I'm sorry, anything below the x-axis, or in this case, this is the t-axis. And the reason? Because this is a projectile that is being fired. And we know projectiles go up in the air. They reach this maximum height right here. And then they come back down to the ground and they hit right there. So this is when the projectile hits the ground. So for me, my restricted domain here is going to be in between. So I'm going to allow t to be in between 0 and I have to go back to Desmos real fast because I forgot to do this. That's okay, we'll live. So it's going to be in between 0 and 4.082. 4.082. So this correlates with that function right there. Anything beyond 4 seconds, don't care. Because theoretically, mathematically speaking, that is going to be inside of the ground. It's going to be below what I want. So you don't worry about it. You restrict your values of t to be in between 0 and, in this case, 4.082. Okay? So that's exactly how this restricted domain stuff works. And you see this all the time within like statistical projects and stuff like that, like regression analysis, because your data is only good for a certain amount of values. Anything outside of that, it kind of gets crazy. Now, we do have other types of functions, all right? And this is called a piecewise defined function. All right. Now, the key word or the root word in this entire or entire definition that I'm about to give you is right here. This is where you have a function that is separated into pieces. All right. So for example, f of x could equal something like this. X to the second when x is less than or equal to 0. And then 3x plus 1 when x is greater than 0. So this is what we call a piecewise defined function. And these are also used everywhere. If you look at your a detailed description of your electrical bill, you will notice that in between certain times, the electrical company charges you different rates. And that's because they know in the summer, towards the end of the day, when the sun starts to go down and all that heat that has been absorbed in the street, the sidewalk, your house, it all starts to come out. And your air conditioner starts to really work overtime. So what ends up happening is they charge you a little bit more money during that time because they know the electricity is in demand. So that's what they do. I can't say I agree with it. That's just the way it is. So anyways, how do we graph a piecewise defined function? I think that's pretty important. So to graph this, it's very simple. You're going to graph this as if nothing happens, as if it's not even broken up into pieces. Please let me show you this first. So what I want you to do is just watch the screen. I'm going to graph in pink, x to the second. So give me a little minute here. I'm going to try to make this look nice and pretty. So here's the graph of x to the second. All right, looks good enough for me. Now, on the right-hand side, these are the restrictions that I must follow. So if I want to use the very first piece, x to the second, I'm only allowed to use this as long as my independent variable, x, is less than or equal to 0. So here's what this means. I'm going to put a solid dot at the value 0, 0, because when x is 0, 0 to the second equals 0. All right, so that's the first thing. And because I'm only allowed to use values of x that are less than or equal to 0, I'm going to erase the right-hand side of this function. And that's because I'm only allowed to use x is less than or equal to 0 for this piece. Now, I'm going to use bright orange for the next one. So now we're going to draw this piece. All right. And I think you can see where this is going. I'm going to just do this as if, this is the first time ever seeing it. We're going to graph 3x plus 1. So that's a linear equation. To graph this, I start at the y-intercept, 0, 1. I'm going to put a dot, and then I'm going to go up 3 and then to the right 1 unit. And like I said, I'm going to graph this as if this is our first time. So that's what it looks like. However, we have a restriction. I'm only allowed to use 3x plus 1 as long as x is greater than 0, which means I cannot include the value of x at 0. So please just watch. I'm going to erase all of this here. Try to fix it. Oh, sorry. Just want to fix this. And since I cannot use the value at 0, what I'm going to do is I'm going to put an open circle. And then I keep all the values of x that are greater than 1. Oh, I'm sorry, greater than 0. So this is what my piecewise defined function looks like. Notice you have two pieces. It all depends on what you're looking at. So now on the right-hand side, we could do something like this. What is f of negative 3? Well, negative 3 is less than 0. So I'm going to use the first piece. So this is going to be the quantity negative 3 to the second, or f of negative 3 equals positive 9. Second example, what about f of 1? Well, 1 is greater than 0, so I use this piece right here. So that's going to be 3 times 1 plus 1, or f of 1 equals 4. And there is your piecewise defined function and how we evaluate them. So the last thing that I want to go over is this concept of a relation. And it's very, very, very simple. Here we have f of x equals x to the second minus x minus 6. Okay? So what I'm going to do is I'm going to give us some x values. So let's find f of 1 and f of 0. Okay? Well, what I'm really saying here is this, and this goes all the way back to that basic definition of a function. We have a set of our independent variables. All right? In this case, they're going to be the numbers 0 and 1. Well, we want to know what are the corresponding dependent values. In other words, we got our domain, we got our range. So the question becomes, how do I go from, let's say, f of 0 over to here? Well, that's called a relation, and that's right here. So this relation, x to the second minus x minus 6, takes a value in the domain and it maps that value into the range. So, f of 0 is going to be negative 6. Why? Upper right-hand corner, f of 0 equals, put my parentheses first, make my substitution. When I substitute in 0, I get 0 to the second minus 0 minus 6, or f of 0 equals negative 6. Same thing here in the second example. Let me get out my other eraser. F of 1, well, that's just going to be, put my parentheses in first, then make my substitution. So we get 1 to the second, which is 1, minus 1 is 0. So we get 0 minus 6, or f of 1 equals negative 6. So that goes over to there. Now, let's see if this even makes sense. So let's go ahead and let's graph this. So we got x to the second minus x minus 6. All right, and give me 1 second here. I'm going to just type in these values. So we got 0, comma, negative 6. All right, we're going to label it. And then we have 1, comma, negative 6. And we'll label that. And there we go. See, notice here, if you don't zoom it, like, let me go back. So if you don't zoom in enough, it kind of looks like, oh, I did something wrong. But if you zoom in, notice that the vertex goes beneath those two values. Okay? So 0, comma, negative 6 and 1, comma, negative 6. And let's go back. Let us go back to Desmos, because I know what you're thinking. You're thinking, wait a minute, they both point to the same value. That is okay. The reason? For each x value in the domain, you get exactly one y value in the range. So the independent value 0 only maps to the number -6. The independent value 1 in the domain only maps or only points to the -6 in the range. Therefore, this is a function. Later on, we're going to figure out when you don't have a function. For now, we got functions. So I hope this made sense, and I'll see you in the next video.